Welcome to the 5.3 homework walkthrough for the fundamental theorem of calculus. Problem 2. Let g of x equal the definite integral from 0 to x of f of t dt, where f is the function whose graph is shown. Evaluate g of x for x equals 0, 1, 2, 3, 4, 5, and 6. Estimate g of 7. Where does it have a max, etc., etc. So this is going to be one of our longer problems from this homework set, really, although if we know that g of x is the integral, it's the area between the graph and the x-axis, where the areas that are underneath the x-axis are counted as negative. So let's do a little bit of a list. So g of 0 is equal to 0. The area from 0 to 0 is 0. G of 1 is this area right here, which is a half. G of 2 would subtract off this area, from 0 to 2, so that's going to be 0, because it's 1/2, and then minus a half. When I go all the way out to 3, I have another minus a half. G of 4 is the area from 0 out to 4, so this minus a half is canceled out by the positive, so it would be 0 again. So this is just because we have some symmetry between those parts so far. Now g of 5 would be the area from here all the way to 5, where these first chunks canceled out. So it's really just the 1 square and a half. So I'm going to call it 3/2 or 1.5, whatever you want to call it. G of 6 then would be basically what value we had for g of 5 plus this area, which looks like 2.5 more. So we're at 1.5 plus 2.5 is 3 is 4. So an area of 4. Now g of 7, so that would be part A. Part B says, well, what's g of 7? Hard thing about this one is that it's curvilicious. And so it'd be the area up to here is 4, where we count some areas as negative. Plus, I don't know, what does this looks like? This is probably like 2/3 of 3, so it's probably about 2. So I'm going to say g of 7 is g of 6, the area up to 6 plus 2 more, so we'll call it 6. Part C, where does it have a max? Where does it have a min? It seems like it has a min at 3. I mean, that's probably the easiest one, right? Does it have a maximum value? For this particular area, it did. Had a maximum value at 7. It also had some other relative maxes, right? Since it went up to 1/2 and then started decreasing as well. Part D, you want to sketch a rough graph of that. So let's just go ahead and I'm going to do it right on top of this picture, right? Makes sense. So I'll sketch in red our g function. So the area would be 0. Well, actually, because the other graph is red, let's do this one in blue. So we had 0 when it was area of 1/2. Is it 0 again? Is that negative 1/2? 0 again. At 5 is at 3/2. 6 is at 4. So it looks something like this. We could say a couple of things about this picture looks like. So if the blue is my g, the red should be the derivative of g, right? And so we'd expect some things here, like if I'm looking, the slope of this blue line is about 1 here. Good, the value of the red is about 1. The slope of the blue is 0. The value of the red is 0. It's negative for a while. Slope of the blue is 0. The value is about 0. Slope is increasing. We could say a little bit more about this edge over here, where I would actually anticipate that this would be leveling off to be flattened. We didn't quite see all those details, but that's what's happening here, because it should be, when it gets to 7, actually sort of flat. So maybe it'd be a little bit better to draw this curving down a little bit like that, since the slope at 7 should be 0. But there you go. Problem 4. Similar, g of x is the integral from 0 to x of f of t dt, where f is a function whose graph is shown. Similar to the last problem, we just want to evaluate g of 0 and g of 6. So g of 0 is clearly 0. Because the area between 0 and there. Now 6, this looks pretty symmetric, right? The area up above looks pretty much like the area down below. So I'm going to go ahead and say g of 6 is also equal to 0, since they would cancel each other out. Part B, estimate g of 1, which would be this area. Oh, that's like 2 and 2.75? I don't know. Let's say approximately, make these squiggles. At 2, we're going to add to that. I don't know, that's about 2 more. At 3, it's plus, maybe like plus 1 more. So we have that. But notice this, because of the symmetry I'm seeing here, g of 4 would back up. So from 2 to 3, I had about an area of about 1 added on. So I'm going to subtract off that same. These, I'm using equals. These should all be approximate. And g of 5 would be about equal to 2.75. Great. On what interval is part C? On what interval is g increasing? Well, it's whenever your f is above the x-axis. So it's from, let's say, 0 to 3. I might use curvy ones here, 0 to 3. Where does g have a max value? Oh, I realized I kind of cut that off a little bit. That should be, where does g have a max value? Seems to have a max value at 3. E, sketch a rough graph. Okay. And then use part E to sketch a graph of g prime. Okay. All right, so it goes from 0 here. Now g of 1 is about 2.75. So I don't know, we got it kind of going up there. This is kind of bad. I guess I should draw my own graph, but we at least have it max out. Something like this, and it kind of comes down. This is about 6-ish, right? And then it comes down each of these until it probably get down to about 0 there, right? So at the very least, if this is my g function, it looks something, maybe not quite, but something like that. And it's bigger than this graph allows, because this should be about 6. We could see that I'd have a slope that's positive, a slope that's 0, a slope that's negative over there. So the takeaway is that my whatever picture I draw for part F should look like the red curve that's already on there. All right, we'll call that a day. Ask your questions in class if there's more. All right, for these problems, we had problems 7 through 10. We want to use the fundamental theorem, part 1, which basically just said the derivative of g, defined like this, from a to x is just what's inside of there, replacing the t's with x's. So, buckle up, kids. Number 7, g prime of x is equal to 1 over x cubed plus 1. Number 8, g prime of x is going from a constant to x, so it would be e to the, I can barely see what that is, x squared minus x, replacing all the t's with x's. Boom. Problem 9, from a constant to a variable s, so g prime, meaning with respect to s, would be s minus s squared to the power of 8. And number 10, with respect to r, so g prime of r, meaning the derivative of g with respect to r, would be square root of r squared plus 4. All right, let's do some of these problems. Let's see, number 19 is the first one here. Rewrite down the problem. We've got an x cubed minus 2x dx. We'll take the antiderivative, plug a negative 1 and 2. So 2 to the 4th over 4 minus 2 squared. Subtract off of that, negative 1 to the 4th over 4 minus negative 1 squared. 2 to the 4th over 4, 2, 4, 8, 16, so that'd be 4 minus 4 minus, and here we got a quarter minus 1, so that's what, 3/4? Something like that. Scroll on down. Number 20. Well, I guess I still need to see number 20. Let's write it down. Integral from negative 1 to 1 of x to the 100 dx. All right. X to the 101 over 101. 1 to the power of 101 is 1 over 101 minus negative 1 to the power of 101 is negative 1. So the 101, because it's an odd number, just kind of ignore it here, over 101. Oh my gosh, I'm in a rush. I'm being sloppy. Equals 2 over 101. Great. Number 23 is the next in line. This fella. Rewrite it down. Integral from 1 to 9. And call it x to the 1/2 dx. That'd be x to the 3/2 and a 2/3 down there. 1 to 9. So the 2/3, I'm just going to hang out for a second. 9 to the 3/2 minus 1 to the 3/2. Whoa, 9 to 3/2 is 27. So you got 26 times 2, 52 cards in the deck, 52 thirds. Number 24. Rewrite it down from 1 to 8. X to the negative 2/3 dx. When I take that antiderivative, add 1 to the exponent, it'd be 1/3. And a 3 to cancel out the 1/3 that comes down. If I take a derivative, 1 to 8. Let's have the 3 hang out for a second. So it'd be, I guess, h to the 1/3 minus 1 to the 1/3, which is 3 times 2 minus 1, which is equal to 3. We don't have much time yet. So for this one, maybe I'll leave this one for the next video.